So my title here is this question that may sound awfully naive. What is the simplest model of an amorphous solid? And when I use the word simplest here, what I have in mind is simplest from the point of view of a theorist. So is there some small number of hypotheses that we can use to explain many features of amorphous solids? So first, okay, what are amorphous solids? Well, they're all around us. There are different examples like foams, like shaving foam, emulsions, which are liquid droplets encased in other liquid droplets. Colloids, often used as a model system, granular matter like sand, glass that could be like window glass or metallic glass that's now of a lot of technological interest. And then there are various biomaterials that could also be considered in this category, although I'm not an expert on that aspect. Okay, so that's a wide variety of materials. You might wonder, okay, why is there anything in common between these materials anyway? But it turns out that they do share a lot of universal features. So let me just showcase a few of them. So one of them is that all these amorphous solids show long-range correlations in their stress field. And so in particular, they have correlations that decay like 1 over r to the dimension of space. So they decay as a power law, and they have this peculiar quadrupolar structure. So there are different examples of this. Here's some early work from sphere packings showing this, this result. Also, here are results from inherent states of a supercooled liquid. So this is for a typical glass former. And these have also been seen in simulations, in experiments. So in experiment, typically you cannot measure the stress field directly, but you can often measure the strain field in model systems. So there are results from granular matter. This is from very nice spectroscopy experiments done in France. There are also several groups working on colloids where they've measured this. So this is from Dave Waitz's group. And there are also results from German groups looking at similar features. So also for photoelastic materials, which are a model for granular matter, there are some evidence of similar features. So these have been seen for a while, and they're sometimes discussed in relation to plasticity, also to something that's called the Eshelby inclusion that I'll get back to a bit later. Then there are also universal features with respect to vibrational properties. So I don't want to explain this in all detail, but the basic idea is that there are extra vibrational modes over what you'd expect if you had a crystal, which is described to a first approximation by the Debye model. So this is shown for different experiments in glasses. And there are evidence for various analogs in other materials where you don't have direct access to the vibrational properties, but you can measure, you can basically take pictures of the material and see how the particles are moving. So for things like granular matter under some vibrations, or for emulsions or colloids. And then there's a very long-standing anomaly for glasses in the thermal conductivity, particularly at very low temperatures, so say below the 1 Kelvin range. It's been discussed since the 70s, basically. So I'm not going to return to this, so I won't discuss it in detail, but it's also still of current interest in several applications. What I will discuss a bit more are the universal behaviors related to the yielding transition. So if you take an amorphous solid and you shear it, that at a large enough shear stress, the solid will break. And as you approach this so-called yielding transition, there are what are called avalanches. So if you look at a stress versus strain curve, like here on the upper left, and you zoom into it, you find that the curve is not smooth, but instead has these more or less straight lines, which are elastic branches where the stress is increasing close to linearly with the strain. And then there are these abrupt drops, the stress drops. Now, basically, to think about what's happening here, basically you have, you're increasing the stress in your amorphous solid. You can have some localized instability. When that instability occurs, it sends an elastic signal out to the rest of the system. And that elastic signal can trigger more instabilities. And so you can have these avalanches of instability, and these stress drops don't have a characteristic size, but instead they have some fat distribution. So typically a scale-free distribution that's shown here for some examples. So this is on a log-log plot. So the straight line here indicates a power law. The exponent of this power law, normally denoted by tau, has a value around 1.12, 1.25. And there's currently no theory that can explain that avalanche exponent. So it's different from what you'd get from different mean field theories. And this has now been seen in various models, so both in molecular dynamics and also in some lattice models. In experiments, you can also see the same type of stress strain curve. So this is from metallic glass. I think it's from like a nanopillar. So it's a very, very small system where you can start to see some of the erratic nature of the stress strain curve. And if you look at the real space structure of these, what's happening when you stress an amorphous solid, then in 2 dimensions, so this is from simulations, you get kind of line-like excitations. In 3 dimensions, there's a lot less available, but again, the excitations are not kind of space filling, they're some subdimensional excitation. So this is all for systems that are supposed to be models for glasses, but there's related phenomena in other materials. So experimentally, this has been looked at in emulsions and colloidal glasses, and then a lot of work for granular matter, which is relevant to faults. So for earthquakes, just at the APS meeting a few weeks ago, I saw a talk about cytoquake, so earthquake-like phenomena in the cytoskeleton. So I think it was quite similar behavior there. So again, quite a universal feature of amorphous solids. So we have these various universal features, and one can ask if there is some small set of hypotheses that we can use to explain them. So what I have in mind is that for crystals, we have this Debye model that identifies the relevant excitations, namely phonons. And once you know that you have phonons, you can compute relatively straightforwardly the density of vibrational states, also the specific heat, and then you can add on to this model the defects in the crystals to understand plasticity and so on. Now, for amorphous solids, we know different modes that are available. So there are phonons at very long wavelengths. You have what I call here extended modes. So these are modes where if you look at the particle motion, it's not like a phonon, like a simple wave. It's more like the particle motion is more like vortex-like motion. So I should have put a picture in here, but I didn't. And then there are also some localized modes, both at low frequency and high frequency. And then you have these various universal features, and we can ask, is there some model that will explain all of these features? Okay. Now, one approach that has been used over the past, say, 20 years, but in fact goes back a bit further to Thorpe in the 80s, Phillips in the 80s, and even Maxwell in the 1880s, is this jamming approach. So the basic idea is that for most amorphous solids, where they're vibrating around some inherent state that's a mechanical stability, mechanical equilibrium. And so let's just take the limit where it's at 0 temperature. So it's just stuck in this state. And for these systems that I mentioned to you, then they're typically dominated by repulsive interactions at short distance. So there may be some longer range attractions that are kind of keeping the whole glass stable, for example, but they're believed to be less important than the short range repulsion. So, okay, there could be amorphous solids where attractions are really important at short range, and then they behave quite differently. But the ones that I mentioned to you are all in this category. So let's take this limit, neglect the long range attractions, and take the 0 temperature limit. Then our model systems are going to be basically elastic networks, like what I'm showing you here on the right, and also sphere packings. And then the idea is to try to use mechanical stability, which you have in that limit, and some aspects of the simple local structure that you get from having an elastic network or a sphere packing to understand general properties of amorphous solids. So basically, once you take this perspective, then if I look at the level of 2 particles, or equivalently for 2 nodes of my network connected by a spring, then there are going to be 2 important control parameters. So the first is the coordination, which is just the average number of strong directions per particle. So I'm denoting these directions along the springs as the strong directions. And then some measure of the importance of the transverse interactions, which can still be there. So I'll call that E, and I'll return back to it in a second. Okay, so I worked in my postdoc with Meteor VR on this approach, and we computed many things. So In particular, a phase diagram of solids basically spanned by these two control parameters, and then predictions for the boson peak, that's the vibrational modes, the spectrum, and then the quantities that the experimentalists actually measure, so the dynamic structure factor, the damping coefficient, and so on, and then also the extension to colloidal systems that I don't have time to describe, and for the experts, it's computed type of approximation. So I don't have time to go into all details, and I want to get to more recent work, but I'll just tell you a little bit about what is the kind of intuition of how these control parameters affect the behavior of amorphous solids. So the first result that goes back all the way to Maxwell a long time ago is that the coordination has to be large enough to be stable. So that's quite intuitive, and that's true in the absence of any stress. The nice result is that if you just have central force interactions, then this critical coordination ZC takes a very simple value. It's just twice the dimension of space. So say in 2 dimensions, Z has to be greater than 4. And what's more recent is that it was shown that at this so-called unjamming point, or it's sometimes called Maxwell point or isostatic point, then BP, this is the boson peak, actually must diverge. So what it means is that this Maxwell point, it's a very singular point where you're going to have very, very sharp anomalous behavior. And in the spirit of other systems in physics, we can use this point to try to understand how it organizes the behavior of the whole solid phase. So real solids are not going to be exactly at this point, but if they're nearby, we can try to understand first what happens at this jamming point and then perturb away from it. Okay, so that's the coordination. And then what about this other parameter that I mentioned? So to understand that, what we can do is we can suppose you have some amorphous solid, and we look at small vibrations around whatever inherent state that we're in. Then you can expand the elastic energy around that state, and you're going to have two terms. So basically, you're going to get a sum over the bonds that you have in your system. And there's one term here, which is just the spring term. So this just involves what I've written here as longitudinal displacement. So displacements along this strong direction, and K is just a spring constant. So this is totally expected. But you also have this second term here that involves displacements in the transverse directions. And the key point is that this term here has a negative coefficient if the forces are repulsive. So what that means is that this term is going to be destabilizing. It just corresponds to the fact that if I have this situation here, if I have some transverse displacement, it increases the bond-to-bond distance, and so it lowers the force, and so that's actually destabilizing. So what I called the contact strain is just the coefficient that measures the importance of this term. So it goes as the force in the bond divided by the spring constant of the bond and divided by a bond length. And so once you have this transverse term, then you can lose rigidity a second way. And that's by increasing this contact strain to some critical value. And this is basically a buckling instability, but it's not buckling kind of the macroscopic scale like Euler buckling, it's kind of buckling in the bulk. And so what you get in the end in this part of the plane of E versus Z is this kind of wedge of a stable region. And Z has to be bigger than this Maxwell point. Maxwell value ZC, and has to be lower than this value. This turns out to be a parabola. Okay. So again, I don't have time to explain all details, but there's a whole parallel story of recent developments. Sorry, I see that my video is all screwed up. So there's a whole parallel story of recent developments that involve the exact solution of various glass models in the mean field limit of infinite dimensions. So involving these people here and others. So Pier Francesco is present here. And what's nice is that the results from that approach are consistent with the results from the jamming approach when they overlap, but they are complementary in many respects. And so I think one can say overall that the mean field understanding of glasses, and I really mean amorphous solids more generally, is in quite good shape. But of course, there are aspects that are missing from this picture. So in particular, we're still missing a description of plasticity and yielding in real space. So for example, to derive that avalanche exponent that I mentioned. And also of interest to me is deriving the continuum equations of plasticity that are used by engineers, which still have never been derived from any macroscopic framework. These approaches don't capture these stress correlations. So they're really missing the real space structure of the inherent states. And although I haven't really talked about it much, they also miss the lowest frequency, lowest temperature regime of vibrational properties. Now, in physics, when we want to go beyond mean field, then there's a set of standard tools which go by the name of field theory. And what's nice about field theory is that if you take any system and coarse grain it, then you can produce some field theory. And what's nice is that the tools of field theory tell you about which things are important and which things are not important. So it's a way to kind of systematically organize your understanding of some class of systems. So this is what I've been working on over the past few years in relation to this problem. And what are the basic ingredients that I believe are important? So the first is that the disorder in this problem is really constrained by mechanical equilibrium. So that's motivated already by this jamming approach. And I'll explain a bit more in a second how that actually is kind of instantiated. And the second point is that when we have anomalous behavior, it's basically because we're approaching some kind of marginal constraint satisfaction. So there is this Maxwell point that leads to what one can call jamming criticality. And we also have this buckling instability, and that leads to another type of anomalous behavior, which, okay, it's called marginal stability if you're really on this point along this line of buckling instability. Okay, so how does that work? So let's take now a continuum point of view. Then mechanical stability requires that the stress tensor is divergence-free and symmetric. And in 2 dimensions, you can exactly solve these relations by writing the stress tensor in terms of some other field, which is called the area stress function. So the details are not so important, but the key point is just that this whole stress tensor, which is some object with 4 components, actually is given just by some derivatives in terms of one scalar function. So if we want to do a theory that's on the inherent states, so in other words, that includes mechanical equilibrium, then it's more parsimonious to, instead of using the stress tensor, to just use this area stress function. And this is in 2 dimensions, but there's an exact analog in 3 dimensions. And so you can work, in other words, on a manifold of metastable states by using this stress function. This leads to what is called the stress ensemble that was first considered in this paper here. And so one can compute various things in this framework. So for example, the long-range stress correlations that were computed with various assumptions in this paper. They were later argued to actually arise from elasticity by Anna Lemaitre. And I want to show you that it really comes very, very naturally from this framework almost immediately. So don't be afraid by the indices here. The key point is that as soon as you have the stress tensor written in terms of this other field, then the full correlation function of the stress tensor, which is some object that has 4 indices, that looks like it's going to be a complete mess, it's just given by some derivatives of this one scalar function, which is the correlation function of the area stress field. And the area stress function is a bit abstract, so you can prefer to think about the pressure. And so equivalently, you can say that the full correlation function of the stress tensor is just given in terms of this pressure correlator. And now, if you use pretty standard field theory arguments, you can arrive at the fact that this pressure correlator is going to be constant in Fourier space with corrections that just appear at the particle scale. And so if something is constant in Fourier space, it's a delta function in real space, and that's exactly what you find. So this is, sorry, my menu is like getting in the way here. So that's what you see here in the upper left. This is from simulations by Anna Lemaitre for a glass. And these other pictures here are just these other anisotropic correlators that all follow exactly as soon as you have this one very simple result. So mechanical equilibrium is really enough to predict the anisotropic structure. And in the spirit of this conference, let me emphasize that how simple the argument is, that basically, as soon as you have some field that's constrained by some equation, then you can often have this type of structure that you'll have long-range correlations that are induced by the constraint that you have. Okay, and from the field theory, you can get more. So you can, for example, get field equations which turn out to be equivalent to linear elasticity. So I did this both in 2 dimensions and 3 dimensions, and I won't dwell on that. So I guess I'm getting over time. So I'll just mention one other thing that I've done recently, which is now that we have a simple theory for the structure of inherent states, one can try to compute the response around those inherent states. And you can do so by kind of crudely modeling the quench process. So basically we have this Gedanken experiment of starting from a homogeneous continuum. You add some random forces, which is mimicking, say that you start with a liquid at finite temperature, and then if you immediately quench to 0 temperature, under the action of those forces, your system is going to find some inherent state. And it's going to end up with some quench stress here. And then you can compute the moduli fluctuations that you get that are Gaussian in agreement with experiments. You can compute the inherent stress distribution, which will recover the previous theory. And you can also then compute the Green's function around your inherent states. And it turns out to exactly recover the mean field results that were derived with a totally different method before. So this type of approach can unify the mean field results that were obtained from the jamming approach with this field theory. So this is work with a brilliant student, Masanori Shimada from the University of Tokyo. And I'm going over time, so I'll just skip.
I will have to cut it short here. We have about 3 minutes left for questions.
Yes.
So, see, there's plenty more to discuss, perhaps for a gather town session. Anyone?
Yeah, so I'll just put up my summary slide, and thanks for listening.
Anyone has a question, please type Q in the chat. No. Thank you for this very interesting talk. So you've shown that your field, I'll start with a question. So you've shown that your field theory captures some of these features of a passive system. And I know you mentioned that you're not an expert on the active system, but I was curious because I am quite interested in active systems, whether or not the stress features to minimal order are the same there, or are they inherently different due to the activity? Because I can imagine that introduces all kinds of, well, perhaps possibly even non-Gaussian noises and so on.
Yeah, so I really know very little, but I do know that there are people who are studying this and trying to make the comparison between more traditional amorphous solids and active systems. So for example, Elizabeth Agaritzis, who is here, and Alessandro Manacorda, who's also here, have been working on related things. So of course, it depends on regimes, but if you're in a regime where you have something that's just fluctuating in a small amount around some structure and mechanical stability, mechanical equilibrium, then you can try to apply the same types of tools. So even if what's causing the fluctuations is something that's, say, active, so it's not the same as a temperature, then you can try to apply some of these tools. If you have something that's not, well, it has to be a solid basically, otherwise then you're going to be in a totally different regime.
Yes, I'm going to go through a couple of the questions still. So Thomas O'Connell? Connor,
Yeah.
sorry.
Hi, my question is just, I didn't quite catch it from the talk. Is this theory a dynamic theory? Like, can you explore applying strain rate fields in your solutions?
So at the moment, no, but one could imagine doing that extension, and that certainly would be of interest. Yeah.
So it's there's an open path towards that.
Yes.
You would imagine. Okay. Cool.
Pier Francisco.
Hey, hi, Eric. Thanks a lot for the great talk. I just wanted to ask you two things that it's not very clear in my mind. So when you say that the mean field approach is misses, for example, stress correlation, then of course this is due to the fact that you are in some kind of large dimensional limit or mean field approximation. But even if you miss the real space correlation, you can always compute susceptibilities that are just integrals of correlations. This you can measure. So from mean field, for example, you can obtain, this is something that we did with Giulio some time ago, you can obtain, for example, the breakdown of elasticity in the susceptibilities, in the elastic susceptibilities. So this is something that maybe you can also test in this field-theoretic approach, just trying to do trying to look at the susceptibilities.
Yeah, that's a good point. So I agree that you could measure this as susceptibility. So Actually, it was done in some experiments on granular matter where they couldn't really resolve the full correlations. So it's kind of easier to measure some integrated thing. So they looked at some integrated measure to kind of to show that you have anomalous correlations, because the integrated measure, well, as a function of distance over that you're integrating over, have some anomaly. So yeah, I agree that that can be a nice way to compare with what you've done with Giulio.